As we settled in to start producing this episode on Monday, we saw on social media that a 7.3 magnitude earthquake struck west of the Indonesian island of Sumatra and triggered a tsunami warning. This particular earthquake didn't particularly cause damage, and after 2 hours, the tsunami alert was called off. While everything seems to have come out okay, it was a reminder that the same factors that make our world livable also make our world capable of great destruction. Our world has inner layers of molten rock and metal on which our outer crust floats and moves. Within these layers, our magnetic field is generated, and it both protects us from high energy particles and aids in the formation of amazing atmospheric aurora. Those molten layers are the source of magma that forms new crust, and they are where old crust gets recycled as our world constantly renews itself through plate tectonics. In the first segment of today's show, we are going to look at how we understand what structures shape the inside of our world and how the inside of our world is constantly reshaping the surface. And we even look at how new hydrothermal vents are still being discovered in the depths of the Atlantic Ocean. While we could spend an entire episode on Earth, there is just too much going on in the universe to linger anywhere too long. From our world, we journey out to look at the supermassive black hole in the core of M87. And then Beth Johnson will join us with an interview of the SETI Institute's Dr. Chenoa Tremblay. And they discuss how radio astronomers are just one step away from being able to simultaneously look for life and do science with a very large array. All this and more is coming to you right here on Escape Velocity Space News. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Back in 1912, a researcher by the name of Alfred Wegener looked at our world and the literal shape of things and wrote a pair of papers putting forward a new theory, plate tectonics. And he used that theory to explain that long ago the land masses of our world were arranged into a single great landmass he named Pangaea. It would take until the 1960s for this scientific understanding of our world to be fully accepted. But in today's era of satellite imagery and corner-to-corner seismic data, no one can deny that the surface of our world is made of plates that are in motion and that the edges of the plates can be traced through volcanism and earthquakes. Since 1912, researchers have been trying to understand how the movement of the plates has influenced the distributions of plants, animals, and minerals. And researchers have also been trying to figure out how the small bits of land manage to rise up or wander off into the sea. In new research in Nature Communications led by Nicholas Reel, researchers look specifically at how motions in the late Cretaceous shaped the Caribbean region we see today. At the time, a land mass called the Caribbean Plateau interrupted the Pacific Plate. Motions of both the plateau and the Pacific Plate into the South American Plate led to the plateau getting locked into place while the Pacific Plate plunged under it. These motions and the Caribbean Plate's lack of motion opened up space for a mantle plume to channel magma to the surface, creating, over the following millions of years, volcanic archipelagos we see today. This particular confluence of motions highlights how sometimes it seems like 1 + 1 can equal 3. In this case, two plates plunged beneath one another and led to new land rising up. While this explanation is straightforward, figuring out this is what was going on was anything but easy. According to co-researcher Boris Kaus, quote, "We are in the unique situation of being able to carry out very realistic simulations," end quote. This research was made possible by the MOGON 2 supercomputer, operated by the Johannes Gutenberg University Mons and the Helmholtz Institute Mons. This is one of the fastest high-performance computers in the world. As so often happens, a lot of our science progresses at the speed of technology. One of the less discussed problems in science is a lack of resources. Some researchers compete for limited time on supercomputers. Others compete for time on telescopes or access to laboratory equipment or even mining equipment in deep-sea submersibles. Luckily for me, telescopes can readily be shared, and as our planet rotates, each facility can get access to its own half of the sky. Folks trying to study the depths of the ocean have to share a limited number of research vessels and submersibles, and they have to go to the specific places they want to study. While 4 astronomers might use a telescope to look at different objects all in one night, one research vessel can only go to one place at a time. Luckily for ocean researchers, a brand new vessel, the Falknor 2, has recently deployed with both autonomous and remotely operated underwater vehicles, capable of mapping the sea floor at 1 meter resolution. During its inaugural expedition, researchers from 11 institutes explored the sea floor along a 434-mile stretch of the Mid-Atlantic Ridge. This underwater mountain range marks the boundary between diverging tectonic plates. Past studies had uncovered amazing hydrothermal vents where heat and chemically rich gases and lava escape into the ocean. At these depths, there is no sunlight, but the heat and the chemistry of the vents is able to support thriving ecosystems. On this expedition, researchers discovered 3 new hydrothermal vent fields, each teeming with life, including swarms of shrimp and even a rare big fin squid. It is often said that what lurks beneath the seas is less understood than what lurks within the stars. I don't think that is true. As a PhD astronomer, I am confident in saying there is a lot we don't know. That said, this vessel is mapping the seafloor at 1 meter resolution, and it is mapping regions that have never been mapped before, and there are still regions unmapped. The Lunar Reconnaissance Orbiter has imaged the moon multiple times at resolutions of 1 meter per pixel or better. We literally have better maps of the moon than we do of the ocean floor. As hard as it is to study the ocean, studying the internal structure of our world is even harder. But it isn't impossible. Earthquakes, for all the damage they can do, also allow us to map the inside of our planet in much the same way sonograms can map a baby. And just like a sonogram can sometimes surprise a parent with a pair of twins, the seismic waves from earthquakes can sometimes surprise scientists. Just not with babies. Not even kaiju babies. Anyways, a research station in Antarctica recorded thousands of seismic waves passing through our planet. The way these waves bend as they travel and the speeds that they travel reflect the kinds of structures they are passing through. In this massive data set, they saw the normal things, the mantle, the core, and they saw something new. A dense, thin, submerged ocean floor that is now hidden beneath the tectonic plates. It's complete with mountains. This ancient structure is the kind of thing we thought got melted down and recycled after it was plunged underneath another plate. We were wrong. This work is led by Samantha Hansen and appears in the journal Science. The data is clear that these structures exist at the core mantle boundary, and by using massive computer simulations, this team is able to show how subducted material can ultimately end up globally distributed throughout the lowermost mantle. I now want to see some weird new version of Pacific Rim where somehow these mountains are where the kaiju come from, or something. Science is so much weirder than fiction, and this result is one of the weirdest about our planet I've read in a while. After the break, we're going to take a look at how machine learning sharpened our view of the region around M87's supermassive black hole. Stay tuned. To our eyes, our night sky is full of stars. To a telescope, there are even more stars. But it very quickly becomes apparent that our sky is spattered with billions and billions of galaxies, stretching out for almost as far as light has had time to travel. In school, we often study key systems that can stand in as the prototype for this system or that. And while prototype is the correct word, it sometimes feels like archetype would make more sense. Let's consider the massive galaxy M87, for instance. Like the king of the galaxies, this system sits in the center of the Virgo cluster's largest clump of galaxies and reigns gravitationally as the most massive system of the more than 2,000 galaxies that make up this cluster. And M87 is growing. Smaller galaxies have regularly merged their mass into M87, and they feed their gas and dust to its actively feeding black hole. Located just 54.5 million light-years away, M87 is close enough for telescopes to study its stars and detect details in its jets. This has made it the go-to galaxy for researchers looking to understand supermassive black holes and their surroundings. In a new paper in the astrophysical journal Letters, researchers Emily Leopold, Shengpei Ma, and Janelle Walsh describe observations from the Keck Observatory of stellar motions in M87. From our perspective here on Earth, M87 looks very spherical. But by looking at how the stars are moving, researchers were able to map out the system's actual 3D structure and show that it is more of a flattened ellipse that is actually tilted toward us. To get to these results, Keck had to point at 62 locations in M87, from the 3,000 light-year across core to the outermost edges, and measure the collective motions of all the stars in each region. As Shengpei Ma explains, quote, "It's sort of like looking at a swarm of 100 billion bees that are going around in their own happy orbits. Though we are looking at them from a distance and can't discern individual bees, we are getting very detailed information about their collective velocities. It's really the superb sensitivity of this spectrograph that allows us to map out M87 so comprehensively." End quote. This new understanding of how the stars are moving allows researchers to better understand the central black hole. As Ma further explains, quote, "Now that we know the direction of the net rotation of stars in M87 and have an updated mass of the black hole, we can combine this information with the amazing data from the Event Horizon Telescope team to constrain the spin. This may point toward a certain direction and range of spin for the black hole, which would be remarkable. We are working on this." End quote. Science is an iterative process. Data from one kind of telescope feeds into how we view data from another telescope. Some of you may remember the 2019 release of the Event Horizon Telescope's image of how M87's supermassive black hole is wrapping light around itself. This image was created by combining light from myriad radio telescopes around the world and synthesizing them into a telescope the size of our planet. Unfortunately, because those telescopes aren't deployed in a perfect circle, there was effectively missing data that prevented the highest possible resolution from being achieved. By combining measurements of the mass of M87 supermassive black hole with advanced machine learning algorithms, researchers synthesized what the missing data should have looked like and tried combining that synthetic data with the actual event horizon data to see if they could improve the image resolution. This is sort of like having two cameras looking at a volcano from different angles, and then using geometry and some basic understanding of what volcanoes should look like to create an artificial image of the volcano from the perspective of an imaginary camera that sees something unique to the other two systems. I have to admit, this feels a bit like using content-aware upscaling tools to create images that show details a camera couldn't actually resolve. However you choose to look at this, the team's result is a less fuzzy ring of light that matches the best possible resolution of the system. And it's consistent with all our other measurements of M87's black hole. This work is also published in the Astrophysical Journal Letters and is led by Leah Medeiros. This paper focuses on how they improved the image resolution, and we look forward to seeing new science results in future papers. Every optical system has its issues, and we have to either accept or correct for them. This was true for the Event Horizon Telescope with its uneven distribution of radio dishes, and this is even true of the JWST and its diffraction spikes. When you look at JWST images, you'll notice a set of 6 primary spikes and 2 lesser spikes stretching away from bright objects. These spikes are caused by the light from each hexagonal mirror interacting to cause 6 equally spaced diffraction spikes, and light from the 3 struts that support the JWST's cameras. Those create another 6 diffraction spikes, of which 2 don't align with the other 6 spikes. The spikes caused by the struts over the mirror are something we see in a lot of other systems, including the Hubble Space Telescope. With HST, there are just 4 spikes, and I have to admit that at this point, my brain can pretty much just filter them out when I look at data. With JWST, these spikes are new and a lot harder to mentally see around. This week, the teams at JWST released a new image of ARP-220, a merging galaxy. This system, shown here using data from the Hubble, allows the keen-eyed viewer to make out faint wispy arms arcing away from a gas-filled core. It is believed that this is a merger between 2 spiral galaxies, and this splotch shows the results of 700 million years of merger and star formation. JWST's image focuses on the core of this system, where it is believed 2 separate supermassive black holes are actively feeding on infalling gas and dust. Unfortunately, this image is dominated by diffraction spikes, which are superimposing themselves on the faint light of the warm gas surrounding the core. This image uses filters designed to capture the light from polycyclic aromatic hydrocarbons as well as light from cool gas. If you focus on the spaces between the spikes, the filigreed structures of star-forming gas are visible, and this science will lead to amazing results. It's just my least favorite JWST image so far, and it makes me really wish we had the capacity to build massive single mirror scopes for space. Someday, large vehicles like Starship may be able to put this kind of instrumentation into orbit, but for now, diffraction spikes. And for now, You know that when you see this pattern of 6 plus 2 lines, you're seeing light interfering with light and making it harder for us to see things clearly. Up next, we're going to have our correspondent Beth Johnson on to interview Chenoa Tremblay about radio science and the SETI Institute. Stay tuned.
Thank you, Pamela. In the search for life beyond Earth, particularly when in relation to exoplanets, one of the methods out there is looking for interesting signals that might signify a technologically advanced civilization. This story is not about that exactly. Recently, a paper was published detailing a repeating signal from a planet called YZ SETI B. And while the repeating signal isn't a sign of aliens, it does tell us that perhaps this planet has a magnetic field, which is incredibly interesting in and of itself. Joining me now to talk about these new results and the search for extraterrestrial intelligence in general is Dr. Chenoa Tremblay, a postdoctoral researcher at the SETI Institute. Thank you for joining us today.
Thanks for having me.
So tell us about this planet, YZ SETI B. What is it? How big is it? Where is it? That kind of thing.
So this is a small planet that's orbiting a star, and it's relatively close to its star. And the star itself is a bit variable. It's a little later in life than our own sun, and so it kind of shoots out some extra radiation than we don't have to deal with from our own solar system. And yeah, so the naming this YZ SETI B, B means it was the second star second planet that was discovered around this star, and the star itself is called YZ SETI.
So we have a. Is this an Earth-like world or like an Earth-sized world?
Good question. I didn't look it up.
So just to be clear, Dr. Tremblay was not involved in this particular research, but you are obviously working at the SETI Institute and the project that you are working on. Will you tell us a little bit about that?
Yeah, I'm working on a couple different searches for extraterrestrial intelligence. So we're looking for radio signals that are not natural in nature. So this paper is a very natural signature. It's a signal that where the waves of light have been joined up due to a magnetic field. Instead of being very random, they're much more aligned. And what we're looking for is something that's non-natural. So typically much narrower than any natural signal from astronomical sources, and indications that there's a civilization out there of sentient beings that have created a signal, whether they're communicating amongst themselves like we do with Voyager or Mars rovers, or something that they've intentionally sent like we did in 1970s with the Arecibo telescope. And so we're looking for those type of non-natural signatures or signals coming from planets similar to the YZ SETI.
So this particular signal is wideband, so it covers a range of wavelengths. And what they're saying is that it is a possible indication that this planet has a magnetic field, which would make it the first exoplanet where we've said that there's a magnetic field that we've detected. Why is that important in the search for extraterrestrial life?
Yeah, there's a lot of these interesting things. So the first time we detected a signal like this was between Jupiter and one of its moons. And yeah, this indication of a magnetic field is important for understanding the ability for the planet to hold on to its atmosphere. So one of the problems that, say, Mars may have had in its past was it didn't have a magnetosphere, so its atmosphere is blown away by the energy that's being produced by the sun, these extra rays. And our own planet has a magnetosphere, which is kind of protecting its atmosphere. What some of the other studies, not in this paper, but other research have suggested that when you have planets around these highly variable stars, which happens to be quite often, is that the chemistry of the atmosphere will be rapidly changing, which makes it really hard to develop life if it doesn't have a stable environment to develop in.
Mhm.
Um, but a lot of these simulations can't quite match in magnetic fields yet. So we don't know exactly what the impact of that is, but it means that it's most likely to be more stable of environment and a more protective environment from the radiation from this nearby star.
So, because this is a rocky exoworld, it it's about the size of Earth, just slightly smaller. Uh, this is a big deal. We've seen these on gas giants, but this is the first sort of rocky world we found this on, and so that makes it particularly exciting. Um, why are we looking at stars like these red dwarf stars if they are such volatile environments for worlds for, what we would look at as, life being able to develop?
One, they're more common. So you if you're playing by the numbers, you go with the what's nearby and what's the most generated, I guess, most common to be found in the night sky or the sky in general. And that's what we find is that these variable stars, these M dwarfs or smaller um, but slightly older stars, are far more prominent, at least in our local galaxy, than we can find other types.
So when you're looking, what sort of well, let me find that question in my head again. What types of worlds, what types of searches are you working on in looking for sort of technological signals?
Yeah, so one of the big projects that I'm working on is a project called COSMIC. It stands for the Commensal Open Source Multimode Interferometric Cluster, which is just, essentially a big computer, which we attach to the back end of the Carl G. Jansky Very Large Array in New Mexico, which is the most is iconic telescope, mostly because of it was featured in the movie Contact.
Of course.
And so we have these 27, 25-meter dishes. They're huge. It's a very sensitive telescope. And what we've set up is a computer system that allows us to look for SETI signals anytime the telescope is observing on the sky. And what we're looking for are very narrow band signals. So this is not going to cover very many wavelengths. So less than what your dial on your radio in your car can actually detect. And we're hoping for these signatures that are non-natural in nature and signs that there is some other intelligent being out there.
That brings me to sort of the next issue. If you have a signal and you see it, what's the process? What do we do from there to confirm that it's not from Earth or that it is? And what's sort of the process of the scientific process of confirming that signal, putting the information out there?
I mean, overall, it's check, check, and check. It's, we want to verify, we have to go through a process of calibrations for our systems.
Mhm.
So our signals coming in are kind of meaningless unless we can relate them to anything else. And so we call that process calibration. So we want to check, did that process go correctly? The did we ever see anything like that before? So maybe we didn't, this is the first time we've noticed it, but maybe it was actually in our data somewhere else. And since we collect so much data and we process it in real time, we collect this into a database. And so we can go back through. Have we ever seen anything like this before?
Mhm.
If that checks out and all of the system itself seems to be operating correctly, then what we've done is put in proposals on a series of other telescopes around the world that would allow us to say, hey, we found something that we think might be interesting. Within the next week, can we go point your telescope to that location in the sky and see if this telescope sees something?
Mhm.
The benefit of having such widely spaced telescopes around the world is that there's a really good chance that if it is us that we found, another, radio signal that is just us communicating, or a drone nearby, or a cell phone, or something like that, that it's not likely going to be the same exact thing that's created it, because it's going to be a different environment, a different part of the world, and possibly
Mhm.
even a different hemisphere of the world. And so we can look and see, can we confirm it? Can we see it again, with using different set of electronics with a different instrument, that's located in a different part of the world. And if we do, great. Now we have to go through and see, how much do we still believe it, and what do we believe about it? And is it still something in the natural astronomical sense,
Mhm.
that we just wasn't aware of? And so then the true fun begins, I guess.
So this is because we're saying that this is a magnetic field interaction. We're talking sort of to relate it back to Earth. This is the sort of thing that would happen that would cause, say, aurora on Earth, right? That would be the visual cue you would have standing on that planet would be like, "Ooh, pretty lights."
Yeah, exactly.
Okay. So, your project, Cosmic, is piggybacking off of the Very Large Array data collection. That is huge, correct? That is collecting a massive amount of data. What is the process for going through some of that data? Are you using machine learning at this point, or are there algorithms in place that sort of like can point to something that looks possibly interesting? Or are you guys, I'm sure you're not having to do this by hand because I think we would all cry. We've done citizen science projects by hand and it's exhausting. So how is Cosmic working? What's the data process like?
So at the moment, since we are new to it, and we want to understand the data structures, and our confidence in the data,
Mhm.
we are doing a bit of this by hand, but not in the looking at every single signal, that comes through the pipeline. It does have a real time algorithm in place
Mhm.
to search for signals of particular characteristics, and then it puts that information to a database in which then we can look at statistically. So, one of the things that we do in this experiment is, instead of just looking at the sky and uh, looking at every source within that field of view of that
Mhm.
sky, what we're doing is we're choosing, sources, or stars in particular, that are the nearest ones in each one of those fields, and
Okay.
just collecting in information towards those.
Mhm.
And then what we also do is, essentially, we squash the whole sky flat. We sum across everything that the antennas can see, and then just look at the total about information that's
Mhm.
received. So this would be kind of like, if you put a bunch of people in a room, just listening and seeing who you hear as the loudest voice overall, or picking certain people to be slightly louder,
Hmm.
by putting a microphone in front of them. So it's kind of in that type of process. And so by doing that, we can compare naturally to those signals. So what we would expect from an astrophysical perspective is, if more than one of those microphones has a voice, then we would say that means it's really close by. So it's probably just a signal from Earth.
Mhm.
But if only one of them is picking it up, then it's likely something that's distant. And then we can say, well, if we squash everything in space and we just look at how things are changing as a function of time, or frequency, or wavelength, then we can say, well, then that should give a signal that's, slightly different than something where we would be focused on. And so if they're both show a signal, then that's promising, but that would mean that you would expect one to be weaker than the other. So we can use some logic pieces like this to find the most interesting signals.
So, kind of to sum up, the criteria are that it's a narrow band signal, that you're only hearing it from one point, right?
Mhm.
And that it's obviously not coming from Earth.
Yes.
Okay. Um, so, let's talk a little bit about your history with SETI research. Obviously, as a postdoctoral researcher, this is a thing that you have been doing for a while. How did you get involved or interested in this? What was your influence for getting into SETI? It is, especially now, it's a little bit more in the forefront and it's a little bit more acceptable. But having been in it for a while, it has definitely gone through a period of, oh, you work in SETI. So how did you end up here?
So in 2014, I started working on a master's degree in Australia at Curtin University.
Mhm.
And in 2016, I switched to working on a PhD. And one Saturday morning, I got an email from the director of the Department of Physics and Astronomy that said, "You know what? I know your main topic is actually studying the chemistry of space. But did you know that for the same information, we could do SETI too? Let's start." And so that's kind of how I got into it. And we started exploring some different ways because what I was doing on my PhD was using low frequency radio telescopes, which kind of look uh, not impressive at all. They tend to be little pieces of metal on the
Mhm.
ground. They observe much closer to what our car radios can pick up. They're like 100 to 500 megahertz in frequency space, so really
Mhm.
long wavelengths. And what I was trying to do is see if we could use low frequency telescopes to study more complicated chemistry in space, where it'd be more stable. And uh, and we realized we could repurpose a lot of the data that I was using to look for signals of interest. And the nice thing about these telescopes at the lower radio frequencies is they have very large field of view.
Mhm.
And so, if you're in more technical speak, they cover about 625 square degrees. What that means in more common is it can fit 1,600 moons inside of the field of view. That's just from one pointing of the telescope. And so they're quite large. In comparison, the VLA sees about 1/12 of the size of the moon anytime it points the telescope. So there's a huge difference there. And that allowed us to kind of search a very large fraction of the sky, about
Mhm.
10 million stars all at once, to look for these signals that may be happening, but at these lower frequencies.
And so the method was pretty much the same. You're looking for a narrow band and you're looking for it to come from basically one location on the sky.
Yes, exactly.
You just had a much wider field of view than you do now.
I did. And what we did was, because we wanted to combine more in time,
Mhm.
is that we can correct for the fact that we know that objects in space are moving at a different speed as us on Earth. And
Mhm.
so the receiver and the transmitter would be moving at different speeds. And so we correct for the chances of that speed difference, which can change which frequency the signal would be coming at us as a function of time. And so you might see in SETI news where you see like the Voyager type signal where it looks like a linear line across the page, and that's that Doppler change. That's the
Mhm.
change in, as a function of time and frequency. And so if we correct for that, we expect everything to just be a single line, and so we can look at a single bin.
That's an interesting point. So recently, the Allen Telescope Array was used to find Voyager on the sky. Were you a part of that? What happened?
I wasn't a part of that, but yes, exactly what it's doing is that we can point our telescope at Voyager, which is one of the furthest human-made electronic signal, and mimic what we would like to see coming from another star system.
Mhm.
The benefit here is we know exactly what frequency to expect to detect it. And so we can look at that and set our telescopes to the right, uh, all the right tunings of frequency and time and things like that, and sensitivity, and go and find that Voyager signal, knowing what we know, and then you know in then you can extrapolate that information into what we don't know, to go find signals somewhere else.
Always good to have at least one point of data that you can look at that works. Um, What is next for you and for Cosmic?
So right now, Cosmic is recording during what they call the Very Large Array All Sky Survey, or VLAS.
Mhm.
And so this is a survey of the sky that's expected to cover every piece of the northern hemisphere from a declination of -40 and above. So everything that we can see from the
Mhm.
telescope. And so with that, that means that we are on sky trying to look at millions of stars at the moment and recording that data. VLAS is almost done recording for this time. The Very Large Array VLA has an opportunity to change to 4 different configurations. And so it's going to be reconfigured soon. And so
Mhm.
now we're going to start recording along with other PI driven science. Whatever their favorite goal is, we're just going to be processing to look for SETI. And so we're going to be covering a much wider frequency range and hopefully some new patches of sky.
That sounds really exciting, and I'm looking forward to hearing about any results that come out of this. So, good luck to you and to your team, and obviously on both fronts, from this side, from the interviewer side, and from the study side. I wish you all the luck, and I,
Thank
I
you.
look forward to talking to you again. So, thank you, Dr. Tremblay, for being here with us today.
Thanks for having me.
Before we can get too excited about exoplanets, we really need to figure out how to consistently get off of our own planet. And it turns out last week's attempt to launch Starship was even messier than we knew. From multiple reports, we've pieced together some basics. There had been concern prior to launch that the booster's engines would ultimately require a flame diverter or other means of protecting the launch pad from damage. A steel plate with water cooling was being constructed but wasn't completed on time, and they thought the pad should survive one firing of the engines. They were wrong. If the engines did cause damage, they assumed the damage would come from the engine flame wearing away the cement. They did not think the flame could shatter the cement. But they were wrong. Cement chunks were flung at high velocities, and debris settled over more than a 6-mile radius. As near as I can tell, they didn't anticipate the area around the launch pad could catch fire. There was fire. About 3 acres of wildlife protected area burned. Most disturbing to me, residents, visitors, and journalists all reported that everything was layered in cement dust, and chunks of both cement and rocket rained down over a large area initially, and chunks of rocket continue to wash onto shore. It's spring. All these disasters have affected fragile birds' nests and, in general, made the start of life for animals a lot messier than it would normally be. It is unclear how long it will take for Starship to get cleared by the FAA to launch again. There are 2 major hurdles. To state the obvious, they are going to need to repair the launch pad and possibly a great deal of the infrastructure around the pad. Images of the tank farm, the set of tanks used to hold various propellants and gases needed for launches, those tanks show massive dents, and it is unknown to our team if any leaks are associated with the dents, or if the structures are otherwise still structurally sound. But that's just the obvious stuff. As part of their filing to get launch permission, SpaceX had to lay out mitigation procedures that they would follow in case of an accident. Right now, those procedures are being followed, and SpaceX is going to need to both document what they have done to restore the surrounding wildlife refuge and how they will prevent this kind of literal disaster from occurring in the future. Basically, they need to prove that as they launch on the regular, they won't be disrupting the wildlife sanctuary every single time. Starship has the potential to accomplish great things. It just needs some more work to get there. At the end of the day, we just have to remember space is hard. It's hard to get off our world, and it is hard to land on other worlds. It is with sadness that I have to report that the Hokuto R mission failed to maintain contact with Earth after making a landing attempt. This mission has its roots in the Google Lunar X Prize competition, and it was the second of the finalist teams to attempt a landing. As a reminder, the Google Lunar X Prize was a competition for a non governmental team to land a vehicle on the moon, then travel 500 meters by whatever means necessary and send back images. That first attempt was made by the Israeli team, Space IL, and that lander, Bereshit, accelerated into the moon's surface due to an error. Hokuto R is from the Japanese team at iSpace. The mission successfully completed their first 8 mission goals, but it is now believed that the mission exhausted its fuel early and was unable to slow down enough during landing and hit the surface too hard. 2 additional missions are currently in development, and the team at iSpace believes lessons learned from Hokuto R will allow the next mission to be a greater success. And speaking of spacecraft, next up, I'm pleased to welcome on aerospace correspondent Eric Mattis for this week's Tales from the Launchpad. Hey, Eric.
Hey, Pamela. First up this week, ISRO launched their 57th PSLV rocket into orbit. On board the rocket were multiple payloads for Singaporean companies, Telios 2 and Lumilite 4. Telios 2 was the main passenger on the mission. The other satellites were much smaller and fit below the main payload adapter. The PSLV has flown like this many times. PSLV C-55 also continues the trend of using the rocket's fourth stage as a satellite in its own right, allowing multiple payloads to fly together without the expense of making an individual satellite for each. The launch in the early morning of April 22nd was successful, deploying the 2 separating payloads into their intended orbits. Telios 2 is a synthetic aperture radar satellite that will be used by the government of Singapore for various purposes. The Lumilite 4 is a CubeSat, a very big CubeSat. This satellite is around 35 centimeters long by 25 centimeters wide. It was developed by a Singaporean university to demonstrate a new communications technology called the High Performance Spaceborne Very High Frequency Data Exchange System. This technology will be used to make ship communication easier. 7 payloads were mounted in the PSLV's fourth stage, forming the PSLV Orbital Experiment Module 2, or POEM-2. This version of the fourth stage has solar panels and special computers to keep the stage pointed at the sun, after its primary mission of separating the satellites into their orbits is complete. The 7 payloads included 2 demonstration CubeSat deployers, an ion engine, and other payloads. All POEM-2 payloads were from Indian companies or universities. The weather was hard on SpaceX this week. They had 3 launches on the schedule, 1 from Vandenberg Space Force Base on the west coast and 2 from the east coast in Florida. The first attempt to launch a batch of Starlink satellites from Vandenberg was scrubbed at T-minus 10 seconds due to an unusual reason. There was risk of landing failure because the seas were too high where the drone ship was located. The next day saw launch success, with better seas and a marine layer obscuring the site. The view from afar was impressive, with the rocket rising out of fog into a clear sky. The landing of the booster on the barge was equally impressive, as the barge had a low layer of clouds over it. As the booster was in its final landing burn, it basically sank into the clouds before poking through them and landing safely. Part of the steps the boosters take after landing is the fuel purge. Normally, they're fairly unremarkable, but this one produced a harmless but impressive fireball. The 2 East Coast launches were also affected by weather. The Falcon Heavy launch carrying the Viasat-3 Americas satellite tried to launch a couple of times near the end of the week, but each attempt was scrubbed due to extreme storms that brought winds, rains, thunderstorms, and even the odd tornado. This same extreme weather also affected the Falcon 9 launch of O3B mPower 2 from Slick 40 at Cape Canaveral Space Force Station, causing a 1-hour delay. As of when we're recording this, O3B mPower 2 left the ground, and we'll tell you about Viasat 3 next week. That's it for launches. Now let's look at some stats. We keep track of orbital launches by launch site, also called spaceport. According to Rocket Launch.Live, so far this year, the USA has had 30 launches, China 17, Kazakhstan 4, India 3, Japan and Russia each have had 2, and French Guiana, Israel, New Zealand, and the United Kingdom each have had 1. Of these 62 launches, there have been 4 failures, reminding us that space is hard.
Space is hard, but some missions make it look easy. The Voyager missions, for instance, were launched in 1977 and are continuing to do science from their locations at the very edge of the solar system. Voyager 2 generally requires more power because it has more working instruments, but its radioisotope thermal electric generator is producing less energy today than in the past. It was looking like the team would need to shut down an instrument to maintain sufficient power. Now, researchers and engineers have sorted how to use reserve power to keep the current instruments going until at least 2026. Next year, the mission team will decide if the same power strategy is needed for Voyager 1. Our kudos go out to the Voyager team. And that's it for now. Good night, everyone. And remember to go out and look up.